Hello, everyone. Welcome to the TIFR CAM Colloquium. Today, we are very pleased to have Professor Michael from ETH Zurich um, to give the talk, and he'll be telling us about bubbling and topological degeneration in the calculus of variations. Over to you.
All right. Thank you very much for the invitation and for the introduction. It's a great pleasure to speak in the colloquium at Bangalore. As I already mentioned in our email conversations, I'm really very glad to be returning to Bangalore, even though only virtually. I was visiting the Tata Institute in 1994, and I must say I remember the hospitality of Adimurti and his colleagues very well, and I'm glad to be back. What I'm going to talk about is bubbling and topological degeneration. So some of you may be familiar with these ideas already, but I will go back to the origins where these ideas first arose in the calculus of variations, and then try to also give you some more recent results and some perspective on open problems that maybe you'll be able to solve. Let's start with topological degeneration. I guess, oops, oh yeah, okay, so here we go. So I guess this idea first came up when looking at minimal surfaces of higher topological type. So you all may know that in 1930, 1931, Douglas and Radeau independently solved the plateau problem for disk-type minimal surfaces. But then in 1939, J.C. Douglas went on to consider this problem for surfaces of higher topological type, so surfaces of higher genus, like a torus with a disk removed. And in this process, he may have been the first geometric analyst to discover topological degeneration. So let's immediately look at a concrete example. To fix ideas, we'll just take a pair of disjoint Jordan curves, gamma 1 and gamma 2, in the Euclidean ambient space R3. And we're looking for minimal surfaces of annulus type. That is defined over an annulus type region, a ball with an interior ball removed from it. So these surfaces can be characterized as critical points of the Dirichlet energy, which I've written down as E of u comma rho. It's just the integral of the norm of gradient u squared over an annulus A rho, where A rho is this region in the plane where a norm of z, so z is a generic point in R2, where norm of z ranges between rho and 1. So rho is the conformal parameter of this annulus, and it is some number between 0 and 1. And the competing surfaces are supposed to satisfy the plateau boundary condition, which I abbreviate as PBC in the following. Which means that the maps that we allow as competitors should map the inner boundary S sub rho, where norm of z equals to rho, to the one curve gamma 1, and the outer boundary S1, where norm of z is equal to 1, to the other curve gamma 2, in a continuous, monotone, and oriented fashion. And oriented here refers to the fact that these curves gamma 1 and gamma 2 can be endowed with an orientation, and the parametrized curve u restricted to one of the boundaries of the annulus should transverse the given curve gamma 1 or gamma 2 in a manner compatible with the given orientation. Okay, so this is a variational problem. Find critical points of this energy. And it turns out, however, that also pairs of disk-type surfaces have to be considered. That is, surfaces or parametric surfaces given by maps U1, U2 from the ball, the Euclidean ball B, where norm of Z is strictly less than 1, that each satisfy a plateau boundary condition on the domain B. So the restriction of Ui to the boundary S1 of the ball should be a continuous monotone and oriented map to the boundary curve gamma I. And for each U1 and U2, we consider the energy E, which is given by the Dirichlet integral of U1 or U2 on the ball. Okay, and then Douglas found his famous theorem for the existence of annulus type minimal surfaces, or more generally, of course, for higher genus surfaces spanning the given contours. He was able to prove that such minimal surfaces exist whenever the Douglas condition is satisfied, which means that the infimum of the energy of surface that are truly of annulus type, so where the conformal parameter rho is between 0 and 1, strictly between 0 and 1, when this infimum is strictly below the infimum of the sum of energies of a degenerate pair of disk-type surfaces. So this is the famous Douglas condition. And of course, there's a condition, a very similar one, for the existence of surfaces of general topological type. Now, this condition is not at all optimal, and it does not give information about the set of all solutions of the plateau problem. And even though here it is already clear that Douglas was thinking of looking at also topologically degenerate annulus type minimal surfaces, the role of these topologically degenerate surfaces consisting of a pair of disk type surfaces, the role of these surfaces is not clear. So let's examine this maybe more closely in a concrete example, where the curves gamma 1, gamma 2 are parallel planar circles of radius 1 sitting on the same axis in R3 and are at a distance d strictly larger than 1. So that you can see this more easily, let me maybe show you a short video where you can actually see this. I somehow have to move these. Yeah, here we go. All right, so here you see a pair of two coaxial planar curves of the same radius at a certain distance, and then we start from distance 0 and we see a soap film which eventually tears and becomes a pair of disk-type minimal surfaces. So we can see that again. These are the annulus-type surfaces, and then they degenerate to a pair of disk-type surfaces. Okay, once more. Yeah, so that's a very concrete example that we can study. At which point exactly does the annulus type minimal surface cease to exist? What happens precisely at this moment? So there's another video that I have where we can study this crucial moment, perhaps with better resolution. I must confess that I can no longer say where I found these videos. I took them from the internet. Somebody gave me a link where I was able to find these videos, but I don't have the link anymore. I don't know exactly where I took these videos from. But if somebody is interested, maybe I can try to look and give you the link by email at a later time. But now let's look at this. So this is the moment just before the annulus type surface ceases to exist. And you see there is also quite an interesting dynamic there when you look at this process of degeneration, how the annulus type surface degenerates into a pair of disks. There seem to be other shapes like spheres forming in the process. And this is really quite interesting, I must say. Okay, so this hopefully gives you an idea what we're looking at. And now we can return to the presentation. So these are the curves gamma 1, gamma 2, and we want to find annulus type minimal surfaces spanning this configuration of curves. And now we can look at the energy the energy that I had defined earlier. And in the case now, this energy can be, for each row between 0 and 1, can be computed explicitly. Because, well, it's plausible, at least. I don't even have an exact proof for this. It's plausible that for each row, the minimizer of the Dirichlet energy is given by the harmonic function u rho, whose restriction to the boundary curve is simply given as follows. I hope you can see the cursor on the screen. So on the inner circle, u rho at the point rho times e to the I theta should simply be given by the point e to I theta, comma 0 in R3, where I represent R3 as the complex plane times R. So the first two components are given in complex notation as e to the I theta. And the third, the Z component, is simply 0. So in the model that I just showed, the Z-axis is pointing in the horizontal direction. So this is the parametrization on the inner curve, and here we have the parametrization u rho on the outer curve, where norm of Z is equal to 1. So u rho of a point e to the I theta should simply be given by e to I theta, comma d. So the second curve is at a distance d from the first curve. So then, with the orientation given by this example, the map u rho satisfies the plateau boundary condition and minimizes the Dirichlet energy for the fixed value rho in this class of functions. And you can compute the Dirichlet energy exactly. It is 2 pi times 1 minus rho divided by 1 plus rho minus d squared divided by 2 log rho. And let's abbreviate these functions as f of rho. And you see here two things. So for d equals 0, the second term vanishes. And you see that when rho is equal to 0, you simply have the value 2 pi, which is the sum of the areas of the two disk type surfaces. For a positive d, there is more interesting behavior of this function f of rho that I will show you in a second. But we can, just by looking at this definition, we can note two things. First of all, for positive d, as rho tends to 0 from the right, the value of f of rho always approaches the value 2 pi. Because log rho, of course, goes to infinity, so this term will vanish. And yeah. Whereas f prime of rho goes to infinity as rho tends to 0, which means that we're approaching the value 2 pi from above. That means also that the pair of disks, the topologically degenerate comparison surface corresponding to rho equals 0, always is a strict relative minimizer of E when we extend the energy as I had noted above. Now, we'll see in the graphic that I'll show in a second that there are between 0 and d star, strictly between, there exist both a relative minimum and relative maximum, rho upper star and rho lower star of the function f, that correspond to a stable catenoid minimal surface or an unstable catenoid, respectively. And the energies are as follows. So the energy of the stable catenoid for the conformal parameter rho lower star is strictly below 2 pi, and the energy of the unstable one is strictly above. So this is the relative max, that's the relative min, at least when the separation distance is small. Then when the separation gets larger, both these values converge to a value beta, which is strictly above the energy 2 pi of the topologically degenerate pair of disks. And this happens when d, in particular, when d approaches the value d star. All right, so let me show you this by looking at the graph of f of rho. I need to switch slides. So here, unfortunately, this slide has a German text. I showed this graph in a presentation that I gave before a German-speaking audience, and I do not have the source files, unfortunately. That's why I have to show you these slides in German. So this is the graph where I scale the energy with 1 over 2 pi, so that we start at 1 here. This is the graph of the function f of rho for small separation distance d. Then, as we increase the distance, you see that this relative maximum indicated by a red cross on the graph now becomes visible. It's always there also for very small d, as I had shown you, but at first it's very, very close to the energy is very, very close to 1. Whereas the minimum is clearly distinguishable. It's this critical point down here. Now we increase the separation distance further, and you see that this unstable critical point, this lifts off, and the stable one has an energy that's going up, and now both of these energies are strictly above 1. So we are already beyond the existence criterion given by the Douglas condition. So you would not find this stable catenoid using the Douglas condition at all. And now we have, at a distance of roughly 1.3254 of the two curve, we have a merging of the two catenoids. And as we increase the distance further, the critical points disappear altogether, and the graph f of rho is given by a strictly increasing curve. I owe these computations and the graphics to my former PhD student, Mario Schulz. He's now at at Münster, and doing fantastic things with minimal surfaces with free boundaries, etc. And he also provided a graphic showing the minimal catenoids and the companion unstable catenoid spanning the pair of curves. So this is for small separation distance, and you see here this band shaded in light brown. This is a stable catenoid corresponding to the minimum value of f of rho. Then as we increase the separation distance, we also are able to look through this outer boundary and perceive the unstable solution corresponding to the relative max of the curve f of rho. And we see that this unstable catenoid has a very, very tight neck. And for a very short distance, for a small separation distance, it almost resembles the pair of disks that are the topologically degenerate minimal surface that's always around. Okay, so now we pull the curves apart, and you see that the two catenoids come closer and closer, and here they've almost merged. This is the critical distance, d equal 1.3254 or whatever it was, where the two catenoids coalesce. And then when we go and increase the distance slightly more, then only the pair of topologically degenerate disks remains. So yeah, I think this graphic beautifully illustrates what's happening. And now, oh, maybe I should go back and indicate, using this graph, indicate what's coming next. So what we will see is that sharpening the Douglas condition, we are forced to consider an extended energy functional, where we take as a further possible value for the conformal parameter rho, the value rho equals 0, and suitably extend the energy to this value by taking the energies, the sum of energies of disk-type surfaces. And if we add this, and in particular, if we add the pair of disk-type minimal surfaces that we get as a further critical point to the problem, then you see that always the Morse relations are satisfied for this variational problem. Whenever there is a max, then there are two minimum type points. And this is a degenerate situation where the Morse relations do not hold. And once you go above this critical separation distance, still the Morse relations hold with this degenerate surface consisting of a pair of disks acting as a minimum for the variational problem. So this really is an example where the Morse relations for a variational problem can be checked very easily. So let's go back now to the main slide. So we've just seen these features of the graph, and now we come to a more general result summarizing what I just said happens in this concrete example. So in 1982, I was able to give a new derivation of the classical Morse identities and Morse theory for disk-type minimal surfaces. And I achieved this by recasting the plateau problem as a variational problem on a convex set. And this way of rephrasing the plateau problem also works for annulus type minimal surfaces, as I showed in 1984, at least when the boundary curves gamma 1 and gamma 2 have disjoint convex hulls. And then using my setup, I was able to rigorously establish all Morse relations and derive a full critical point theory for annulus type minimal surfaces in the enlarged space M, where I consider not only annulus type surfaces, U with a conformal parameter rho strictly between 0 and 1, but where I also allow topologically degenerate surfaces for rho equals 0, consisting of a pair of surfaces U1, U2, satisfying the plateau boundary condition. And then afterwards, jointly with Jürgen Joost in 1991, we extended the result even further and were able to deal with domains of arbitrary genus and connectivity, and allowing and including the contributions to the Morse inequalities coming from surfaces of lower topological type. And I guess this is a very, very satisfying way of dealing with this topological degeneration in this classical problem. Now, another key word in the title was bubbling, and this first came up in the context of harmonic maps, again of surfaces. So the domains, again, is a two-dimensional domain. Now, however, it's a closed surface, so no boundary. And we assume that this surface S is endowed with a Riemannian metric G. And then we also take some smooth closed target manifold. For instance, you can take N to be the sphere just to have something concrete to think about. And we're then looking at maps U from the surface S to the target N. And just to simplify, we'll assume that N is a submanifold of some Euclidean ambient space Rn. So these maps are simply vector-valued functions defined on S, such that at every point on S, the value U of X is a point in N. So harmonic maps, weakly harmonic maps, are critical points, again, of the Dirichlet energy. But now, of course, U is a vector-valued function, and we're integrating with respect to the volume, the area measure given by the Riemannian metric G on the surface S. So there are harmonic maps are critical points of this Dirichlet energy in the class of Sobolev functions H1s, n, which is just the class of functions U with finite Dirichlet energy mapping S into Rn such that pointwise the target constraint is satisfied almost everywhere. Okay, and now happens that in 2 dimensions, by a result of Frédéric Hélin, weakly harmonic maps from S to N, in fact, are smooth and are classical solutions of the corresponding Euler-Lagrange equation, which is an elliptic system, which you can write down in this way using the second fundamental form A of the target manifold viewed as a submanifold of the ambient Euclidean Rn, and where delta G is the Laplacian on S in the metric G. This elliptic system just states the condition that the Laplacian of U, which you evaluate on all of the components individually, and then you get a vector consisting of the values of Laplacian of U1 up to UN at every point. This vector should be always orthogonal to the tangent space of the target manifold. So the horizontal component of the Laplacian should vanish. So it's a generalization of the condition defining harmonic functions where Laplacian U equals 0. Here you have an additional target constraint giving you this quadratic term, quadratic expression in the gradient. All right, now a classical problem was posed by Eels and Sampson in 1965. And this is the following problem. They asked, can every homotopy class of smooth maps from U from S to the given target be represented by a harmonic map? So given any map U from S to N, is there a harmonic map homotopic to U in? And Eels-Sampson were able to answer this question in the case when N has non-positive sectional curvature. And in fact, their answer even holds in arbitrary, in the case when S is of arbitrary dimension, it would also hold in dimensions bigger than 2. But we'll now restrict to 2-dimensional domain surfaces. And then the restriction on the curvature of the target manifold is quite severe. For instance, it excludes the case when the target is a sphere. It even excludes any concrete target surface embedded. Closed means compact, bounded, and bounded as a submanifold of Rn, because such a closed target would have to have a point where the sectional curvature is positive. But in 1981, Sachs and Uhlenbeck found the following result. Now we're again in 2 dimensions, and we let S and N be closed as before, and suppose now that the second fundamental group of the target is 0. So N could, for instance, be the 3-sphere, but not the 2-sphere, because for the 2-sphere, this topological condition would not hold. But for 3 or 4-sphere, the second fundamental group vanishes, so this would be okay. Then, for any smooth U0 from S to N, there's a smooth harmonic map representing U0 in homotopy class. And the proof that Sachs-Uhlenbeck gave is presents us with the first example of bubbling in the calculus of variation. Well, there's a simultaneous result of Wente dealing with surfaces of prescribed constant mean curvature. But let's not theorize about priority here. So the Sachs-Uhlenbeck approach is via approximate harmonic maps that minimize an approximate Dirichlet energy given here. So for any alpha strictly larger than 1, we define E alpha of u to be essentially the integral of gradient due to the 2 alpha. So we take a power strictly larger than 2 in which we measure the Dirichlet energy. And because of the Sobolev embedding from W1 to alpha into C0, in this space, for any alpha strictly larger than 1, homotopy classes are well defined. And moreover, the standard lower semi-continuity results for E alpha, for any alpha strictly larger than 1, there is a minimizer U alpha in the homotopy class of U0. Now, for smooth maps, it's clear that as alpha tends to 1, E alpha of U converges to the Dirichlet energy of U. Now, luckily, such smooth maps are dense in the Sobolev space H1 of maps from S to N, and therefore, as alpha converges to 1 from above, we see that the infimum of the E alpha energy in a homotopy class given by U0 converges to the infimum of the Dirichlet energy. And of course, also by the density of smooth maps, we can define homotopy classes of homotopy classes of maps also in the Sobolev space H1. And we'll call this latter infimum beta 0. Now, of course, the hope is that as alpha tends to 1, the minimizers U alpha for the E alpha energy in the homotopy class of U0 will tend to harmonic map a minimizer in the space H1 of maps homotopic to U0. But something could get in the way. Of course, there's always the possibility that we do have convergence, that U alpha k for suitable alpha k tending to 1 converges smoothly to some limit U infinity, which would then be the desired harmonic map. So that would be the nice case or the case of compactness. Or Sachs-Uhlenbeck show that there exist concentration points pk in the domain such that for smaller and smaller radii rk in geodesic coordinates around pk equals 0, the rescaled maps uk of rkx, so we're rescaling with these parameters rk, vk equal uk of rkx converges to some limit v infinity, even in C2 locally on R2, where this limit v infinity is a smooth, non-constant harmonic map from R2 into the target N. So since we're blowing up the tangent space near the point of the domain S near the point pk, the domain of v infinity will be R2, no matter what the original shape or topology of the domain S was. And the Dirichlet energy of V infinity is finite because you can compute the energy of V infinity is, of course, the limit of the energy of V infinity on balls BR when you let R tend to 0. And on each finite ball BR, we have C2 convergence. So EV infinity R2 is less than the lim as R tends to infinity of the lim inf of the energy of Vk on any ball BR. And Vk is just the rescaled UK. So the Dirichlet energy scales invariantly, and as you increase alpha, you can bound the Dirichlet energy from above by the E alpha energy. So you have a bound by the alpha k energy of the minimizer UK equal U alpha k for the alpha k energy. So V infinity has finite energy, and by conformal invariance of the Dirichlet integral, we can lift V infinity to a map from the sphere, which we call W infinity, by means of the stereographic projection from a point P0, say the South Pole. And this map W0 then will be defined on S2 minus the South Pole and will have finite Dirichlet integral. And it will be a smooth, non-constant harmonic map. And Sachs-Uhlenbeck then also show that in this setting for smooth, non-constant harmonic maps with finite Dirichlet integral, the singularity at the point P0 can be lifted, and the map therefore can be smoothly extended to a non-constant harmonic map W infinity from the sphere S2 to our given target. This is what you would call a bubble, simply because the domain now is the sphere and spherical maps are bubbles. All right, so each bubble has an energy E of W infinity strictly bounded from below. There's some number depending only on the target, some number epsilon 0, such that E W infinity is larger than epsilon 0, strictly positive. Now, let's see how the Sachs-Uhlenbeck result follows from this bubbling compactness alternative. So here I have drawn a sketch for you. I will first read what is written on the left of this sketch, so you can already kind of picture what is going on, and then we'll zoom into the slide so that you can see also the graphics. So what we will do is that whenever a bubble forms, we will replace the large part of this bubble inside a suitable coordinate neighborhood around the concentration point by the small part of the bubble, and thus save some portion of energy, roughly given by this number epsilon 0 up there. So we will strictly reduce the energy of the competitor maps, and then obtain a map UK tilde, which has an energy strictly less than the infimum of the Dirichlet energy in the homotopy class of our given map U0 that we hope to find in the homotopy class of which we hope to find a harmonic representative. Okay, so let's now zoom in this graphics. Oops, I hope you can see part of my screen is being covered by the images of the audience. This is probably a feature of Zoom. I hope you can see the graphics. So here we are at the concentration point pK. And we choose coordinates so that pk in our coordinate system is corresponds to x equals 0. Then we have this small radius rk, and we're looking at a scale L times RK. So we just take still small ball, but of size L times RK. So RK is tending to 0. For fixed L, the ball of size LRK will be arbitrarily small when K is large, certainly contained in a coordinate neighborhood of the point PK. So originally, the map UK is given by whatever the blue shaded thing does. So UK maps this interior part of the ball of radius LRK to our target manifold. Now we scale this ball, we blow up with the parameter RK, then the interior radius, this little RK becomes 1, and the radius of the big thing now is L. This is Vk. And as L tends to infinity, the domain now will exhaust whole of R2, and we get a map defined in the limit. We'll get a map defined on all of R2. Now this map, the limit map, we lift to the sphere by a stereographic projection to obtain this W infinity. So we now have this here as our domain of the map W infinity. And there is the blue part of the domain, which corresponds to the interior of the ball of radius L. And we replace the map W infinity on the blue part with W infinity on the red part. So we'll place the large part of the sphere by the small part of the sphere. And in this way, we replace then the map Vk by something which much lower energy, and we scale back and obtain the map UK tilde. Okay, so I hope this illustrates how we define UK tilde. And now, since we assume that the second fundamental group of the target vanishes, the map UK tilde, which only differs from UK by changing the top part of the map W infinity with the lower part, which is the topological change amounts to a map from the 2 sphere to n. So there is, since pi2 of n is 0, there is no topological change, and UK tilde is still homotopic to U0. And it has an energy strictly less than beta 0. A contradiction results, and that shows that bubbling is impossible, and we're left with compactness. The minimizers for the alpha energy converge to a smooth harmonic map as k tends to infinity, which and the limit is homotopic to U0, is harmonic, and achieves the infimum of the energy beta 0. So I later gave a different proof of this result using the heat flow. So the original idea of Eels and Sampson, and I was able to make it work in the two-dimensional setting by also, of course, transferring the ideas of Sachs-Uhlenbeck about bubbling now to the dynamic setting. And this heat flow of harmonic maps of surfaces has attracted quite a lot of attention. All right. So, so far, we've only looked at solutions which are in some sense minima. So the stable catenoids, the minimizing harmonic maps. But bubbling is ubiquitous in characters of variations in geometric analysis, and of course also non-minimizing solutions of variational problems can sometimes be obtained, even though a priori there may be bubbling. So let's illustrate this with Nirenberg's problem. It's about metrics of prescribed Gauss curvature on a closed surface. Again, we have a two-dimensional setting. So because of the Gauss equation for a conformal metric in the form e to the 2UG0, the Gauss curvature is given by this. And now we are on the standard 2 sphere, so G0 is the round spherical metric, and Laplace 0 refers to the standard Laplacian on the sphere. And therefore, if you want to find a conformal metric having a given function f as its Gauss curvature, you need to solve a nonlinear elliptic equation, namely Laplacian u plus 1 equal f times e to the 2u. And this is quite intricate. So there are a number of geometric constraints in the case of the sphere. For instance, the Gauss-Bonnet identity tells you that the function f, if you want to be able to solve 2, then f has to be positive at least somewhere, and we'll simply assume that f is strictly positive throughout the following. Now, you can give a variational formulation to the equation that you want to solve. So you first can introduce the Liouville energy. Its first variation will give you the left-hand side of equation 2. And then we'll introduce the F energy, EU or EF of U, which is the Liouville energy minus this term. Then solutions of 2 can be characterized as critical points of E. And those of you who have looked at this problem will immediately say that there is conformal invariance. So the Möbius group of conformal diffeomorphisms of S2 acts on the problem. And we can, in particular, we can do conformal dilations from a point P on the sphere by taking stereographic projection from the point minus P to the plane, dilating with the parameter T, and then mapping back using the inverse of stereographic projection phi P. Then as T tends to infinity, the inverse of phi pt converges to P in pointwise sense away from minus P. All right, and just let's look at the effect of this conformal dilation. We change our comparison map as follows. For given U, we let UPT be this map U composed with phi pt plus log of this conformal, the square root of the determinant of d phi. And Chang Yang in 1987 already showed conformal invariance of the Liouville energy. And thus the F energy will change as follows. So the Liouville energy is the same as the unscaled energy. But here, if we do the transformation from the original coordinates to stereographic coordinates, scaled stereographic coordinates, we get F composed with phi pt inverse, which as t tends to infinity converges to f at the point P. So it just goes to the functional EFP of U. And that scaling suggests that for large T, the derivative of E and second variation of E at the scaled map UPT are related to the gradient of F and the second derivative of F at the point P, respectively. And this gives the following result. Suppose that F is positive, smooth, and satisfies the condition that the Laplacian does not vanish at any critical point of F. Then, if this sum of indices of critical points of F where the Laplacian is negative, and you take -1 to the index of the point P, you sum over all these critical points and take -1 to the index of the point P. If the sum is different from 1, then there is a smooth solution U22. And this result basically also is a consequence of a bubbling analysis, which says that for almost critical points, the Liouville energy will be almost the Liouville energy of the spherical metric. And so the energy of U will almost be given by this energy with a fixed value F of P. And then this index count gives you the right condition. So let me just conclude with some remarks and open problems. For F not identically equal to 1, no solution of the prescribed curvature problem is a relative minimizer of U. So the Chang-Yang result gives you non-minimal solutions. In fact, the condition, the index count condition in general is optimal. So it's not only a sufficient condition, but it is also in general necessary. This is something that I showed by giving examples. The condition can be interpreted as a Morse identity, which relates the topological degree of the set of admissible functions, which is the set of H1 functions, and it's a Banach space, so it's a contractible set, with the sum of the topological degrees of all critical points of E that can be attained by minimizing or minimaximizing sequences. So the critical points at infinity whose index gives the left-hand side of 4, they play the same role as the topologically degenerate solution consisting of a pair of disks in the Douglas theorem. So if the contribution from the topologically degenerate critical points, if that is different from 1, there has to be a further contribution from a real solution. So you could then ask the question, oops, whether with this interpretation, one can also find examples of functions where you have multiple solutions of the prescribed curvature problem, and perhaps characterize all solutions in the sense of Morse theory. So I think my time is up. We did start a little late, and I also have 2 more examples that I had planned to briefly talk about, but since you had asked me to make this talk accessible also to a wider audience, I think I will finish here and just go to the last slide of my talk. Thank you for your attention. And if you want to read details and find references to papers that are relevant for this talk, you can go to this open source reference. Thank you very much.
Let's thank Professor Michael for this wonderful talk. Now I open the floor for questions and remarks. So there's a question which I had asked you yesterday, in fact, as well, about the
Right.
dynamics. So do you have any comments on that, or is this something which has been studied a lot? Or?
So yeah, you are referring now. Let me just go back to this video. Yeah. So you were referring, I think, to this video where you see the dynamics of the degeneration of the annulus surface to a pair of disks. In fact, I don't know of any mathematical treatment studying this dynamics. Yeah, I think you really want to study the gradient flow for this enlarged energy E of U rho in the setting where D is either at the critical value of at the critical separation or slightly above it already. And then since there is just an unstable critical point, then probably near that critical point, if you're just very, very close, but not at the annulus type surface, you'll be drawn away to the pair of disks. Yeah, so it's like studying a gradient flow in this for the functional EU rho in the set where you not only allow the parameterization U, but also the conformal parameter rho to evolve.
I see.
Yeah, and there are, of course, various ways of modeling this dynamics. So there's the pseudo-gradient flow that I introduced in the abstract, most theoretical paper in 1984. But this is not a natural gradient flow. The natural gradient flow would probably be more in the style of an L2 gradient flow, like the harmonic map heat flow in the harmonic map setting. But I don't know if anybody has studied this. It would be quite a cute problem to look at.
Yeah, it seems quite curious. Are there other questions from the audience? All right, so let's thank Professor Michael again. Thank you very much for the wonderful presentation.
My pleasure. Thank you very much for your attention again.
Will it be possible for you to share the slides of this talk? And wait, I should stop recording first of all.